Okay, as we continue on in chapter 4, we're talking about integration. And we're going to start talking about Riemann sums and definite integrals. We talked about in section 1 this idea of indefinite integrals. Now we're going to look at what we call a definite integrals. We're going to use Riemann sums, which is going to build on what we did in section 2 with this idea of area. So we're going to understand the definition of what a Riemann sum is. We're going to evaluate what we call a definite integral using limits, because you knew limits were going to come up. Right? Well, we've been doing limits already a little bit in area part. And then we're going to define the integral using the property of definite integrals. So we're going to learn a kind of like we did with differentiation. Here we're going to have a basic way to a limit definition to find this. We're going to practice finding this and then find some rules, some properties that make it easier to do some situations. So start off thinking about what we did in section 2. We have the area between the graph of y equals the square root of x and the x-axis on the interval 0 to 1. So again, last section we have this definition. That area is the limit as n approaches infinity of the sum as I equals 1 to n of f of some c sub I times delta x, where delta x is the width of each interval and c sub I is a x value on each interval as you go through your n intervals here. So we go with this idea of equal subdivisions. So delta x is going to take, the width of the interval, which is 1, divided by n. So we'll use the right endpoint for c sub I. That's often the easiest way to go. And we get this limit here, the limit of n approaches infinity of the sum as I equals 1 to n of the square root of I over n. And now here's our problem, because 1 over n is still a constant for my summation, so I can pull that out, but I do not have any formulas for the sum of a square root. So working this out, we do not have a handy formula we can work in. That's going to make things a lot harder. So we want to make finding that square root easier. Let's make it easier. What if we don't use equal intervals? So here's my square root function when x is going from 0 to 1. If we make my c sub I, and again, I'm going to use the right side of the interval, and I'm going to use this I squared over n squared. So we have 1 over n squared, 4 over n squared, 9 over n squared, 16 over n squared. We keep going until we get to n squared over n squared, which is 1. So we can divide that up, and we can take the square root of I squared over n squared. That's what we're trying to do here. Now, in this case, I don't have equal widths of my intervals. You notice each one is different. So I'm going to have, instead of delta x, I'm going to have delta x sub I because I have a different width for every interval. So I just take c sub I minus c sub I minus 1. I can work that out to 2I minus 1 over n squared. And that gives us this now. It's a little messier, but where this radical is, it's taking the square root of a perfect square. And I know I and n are both going to be positive, so I don't care about that fact. So I can figure out this. Make this I over n, and then work out that limit. So we have a constant of n 1 over n cubed. Take that out. Again, it's a constant for the summation, not for the limit. But so we can't pull it all the way out, but we can pull it out this far. Use our formulas and simplify this down. And we notice here, when we take the limit as n goes to infinity, we can just kind of use this idea of, hey, look at the highest term, it's a third degree over a third degree, so we take the ratio 4 over 6, or we can do, hey, let's multiply, or take each top and bottom by 1 over n cubed, and get those down to, you know, the way we officially did that, but yeah, it's 2/3. And that kind of, if you look at this picture, again, this makes sense, because here we're going from 0 to 1, this is 0 to 1, so this whole area would be 1, so it's going to be less than 1. If we put a diagonal through here, this would be 1/2. It's more than a half. So 2/3 sounds reasonable. And we can do this because we're changing this delta x for each time. But the biggest delta x, if we look at 2i minus 1 over n squared, as n goes to infinity, it doesn't matter how big I gets, this is still going to be 0, because it's a first degree over a second degree. So we can still do this. Our limit process works. So this is what we call a Reimann sum. Reimann sum is still this idea of adding up the rectangles. But we're just saying that the width of each individual rectangle, each individual interval, is going to, can be different. So we start, x sub 0 is a, x sub n is b, and all the ones in between there go in order. So x sub 1 is bigger than 0, x sub 2 is bigger than x sub 1, x sub 3 is bigger than x sub 2, so on and so forth. So we're just kind of going along the way. We don't have any overlap. We don't backtrack any of these. But we have to use, instead of just plain delta x, we use delta x sub I, and that's just x sub I minus 1 to x sub I. That's the interval we're talking about. How wide is it? So we take the difference. And then the Reimann sum is, again, the sum is I equals 1 to n, f of c of I times delta x sub I. The main difference, again, on here is that your x sub I is not constant. So that is also going to be a function of I. But this is what's called a Reimann sum for the partition delta. And when we just say this delta without anything else, we're talking about a specific partitioning of your interval. So when we talk about these Reimann sums, we talk about the norm. The norm, we represent it with this. It's kind of like the absolute value, except it has the double bars on each side. You might recognize this. We use the same notation in physics for magnitude. So when we're talking about the norm, we're talking about the biggest interval, subinterval of the, of the total interval. If all of them are the same width, we call this a regular, and we get the norm is b minus a over n. That's what we were using last section. We were actually doing Reimann sums, but we were doing a regular partition to which the norm would be the same as everything else because they're all the same width. In general, the norm is related to the number of subintervals this way. So the smallest number of subdivisions would be b minus a over n. So if they're all the same, it's going to be b minus a over n. If they're not, your norm is going to kind of define, well, the smallest way you can do it is break it up into equal partitions of that biggest interval. If you have smaller partitions, you can break it up into more. So that's why n has to be bigger than or equal to. Because again, a regular partition, it's going to equal n. So when we're dealing with this, as the norm approaches 0, n is going to approach infinity. Because if you look at this, again, if this denominator, if it's getting closer and closer to 0, the smallest value of n is getting closer and closer to infinity. So when this approaches 0, n approaches infinity. But it's not necessarily true the other way. If n approaches infinity, the norm does not necessarily approach 0. So, for example, here's A, here's B. Here's one of my intervals, and this one is going to give me my norm. But that doesn't mean that the rest of these are going to be smaller. And I could break this second portion up into an infinite number of intervals. And then I have this big honking one on the end. So my n can still approach infinity over here, but my norm is staying put. My biggest interval doesn't change. So just because n approaches infinity doesn't mean the norm approaches 0. But if the norm approaches 0, then we can say n also approaches infinity. But if it's a regular partition, then we can go either way. Then n approaches infinity means the norm approaches 0, or the norm approaches 0 means n approaches infinity. Only for a regular partition. So, that's what a Reimann sum is. And again, we've been doing Reimann sums. We've just been using regular intervals, regular partitions, which makes it a lot easier when that can work. And when it doesn't work, then we look for other ways. And sometimes if we're doing this numerically, we might just do Reimann sums. We might go and say, let's break this up into different shapes and then add those all together. But this idea of a definite integral comes from doing this. F is defined on a closed interval, a to b, limit of the Reimann sums over a partition exists. So we look at this as the norm approaches 0, the sum of the Reimann sums. If this limit exists, f is said to be integrable. And I always have trouble saying that word for some reason. It's integrable on AB, and the limit is defined by this, as the norm approaches 0 of the Reimann sum, is defined with this, the integral from A to B of f of x dx. This is what we call a definite integral. A is the lower limit of integration. B is the upper limit of integration. Now, it looks a whole lot like our indefinite integrals we did in section 1. We got this same funky elongated S symbol. We have f of x dx. But the big difference is here. When we do the indefinite integral, we are finding a family of functions. The answer to this is going to be another function. And it's actually going to be an infinite number of functions because we always have that plus c on that. When we do a definite integral, we're not looking at we are looking on a closed interval from A to B, and my answer is going to be a single number. It's not going to be a function, it's going to be a number. Now, there is a connection between these two, which is why we can use similar notation for them. We're not going to talk about that in this section. We'll get into that in the next section. But one of the first things I just want to emphasize is that although they look the same, their answers look very different because one is giving you an equation, one is giving you a family of functions. There's an infinite number of answers to the indefinite integral. There is only a single answer to a definite integral. So, if a function is continuous on a closed integral, interval, then f is integrable on that interval. So again, continuity is really important, is a key. If it is continuous, that means we can find the integral, the definite integral. So let's do one of these. Now, so our definite integral is defined as the limit as the norm approaches 0 of the Riemann sum So this is what we need to do to evaluate this integral. Now, we're going to start off with, because it's always nice to make it's easier to do with a regular partition. So we're just going to go delta x is b minus a over n, which is going to be 3 over n. We're going to, again, use the right side because that's often the easiest way to do it. So my c sub I is going to be, we have this 3i over n, but we have to start with the beginning of my interval. So I have negative 2 plus 3i over n. So what I want to find is, and again, since I say the norm approaches 0 is going to be the same as n approaches infinity, now I'm getting down to what I want to evaluate is the limit as n approaches infinity of the sum as I equals 1 to n of 2 times negative 2 plus 3i over n times 3 over n. And looking at that, I got to multiply times 2. I have multiplied by 3 over n. Those are all constants. So I can take the limit as n approaches infinity of 6 over n times the summation as I equals 1 to n of a negative 2 plus 3i over n. So we get 6 over n times, and what? We got the sum I equals 1 to n of negative 2, plus here 3 over n is my constant, so I'm going to go 3 over n times the sum as I equals 1 to n of I. So that's going to be 6 over n times negative 2n plus 3 over n times n plus 1 over 2. So I'm going to go 6 over n times a negative 2n is going to be negative 12. So I got 6. Here, let's cross out those n's to make this a little easier. I got 6 times 3 times n. I got 6 times 3 times 1 I got n times 2. So again, let's make this 2n and make this 2n. And these will cancel. So this is going to be 9. And as I take the limit, this will go to 0. So I get negative 12 plus 9 equals negative 3. So this integral, as we go from negative 2 to 1 of 2x dx, equals a negative 3. Can it be negative? Because when we did this before, we were finding the area when we did this limit of the function times delta x. We got the area, and can an area be negative? Now things are looking funky, right? Let's look at this graph and see what's happening. If I go 2x from negative 2 to 1, you notice down here, everything's negative. So when I take f of x dx, this is going to give me negative values. So it's going to find this whole area, and this whole area, it's going to count as negative because it's going down. This area is going to be positive, so this is going to take this chunk out of here. And it makes sense in a way. Because if we take this, 2 times 4 is 8, 1/2 base times height. This is a negative 4 here. And we take 1/2 base times height. This is going to go 2 times 1 times 1/2 is 1. This is an area of 1. And we take 1 and a negative 4. We get a negative 3. When we take a definite integral, it's positive to get a negative value. So that's one thing that we have to realize. This is right. There's just one little difference between this and those problems we were looking at yesterday or in the previous section with area, and that's here. Yesterday when we were talking about the area under a curve, we said we had to be non-negative for the closed interval. So if I am continuous and non-negative on the closed interval, then this definite integral is going to give you the area of the region bounded by the graph, the x-axis, and the vertical lines. X equals A, x equals B. If f is not non-negative over the entire interval, it will not give you that area because of that canceling out. It doesn't mean we can't find the definite integral. We still can find the definite integral, and the definite integral still has uses. But it's not just giving us the area bounded by the curve and the x-axis. So that's one thing to keep in mind. I'm going to break up this video here, and we'll pick up in part 2 because I have another lengthy example to go through working with this, and then kind of talk about those properties. So see you for part 2.